Hello, everyone. So let's start. There was a doubt clearing session yesterday, and I have already put up the videos and the slides for that session. So if you couldn't take part, please just watch those. There were a bunch of questions that I have to address that people asked in that session. So one question was about the first homework. In exercise 2, we ask you whether the given encryption scheme and decryption scheme is valid, and the question was, what does valid here mean? Well, it basically means that if you encrypt something with the key K and then you decrypt it with the same key, you will get your original message. That's the idea of validity in that encryption scheme. And another question was about resubmissions. Generally, you don't need to resubmit right now. You can wait until the deadline passes, and then we will give feedback to everyone. And only after everyone have received their feedback, we will open the assignments for resubmission, and you will have at least 10 days. So don't worry about that at all. And finally, there was a question about the data that is being propagated on the blockchain. I will cover that in more detail today, but specifically people asked about what happens with the Merkle trees. And the answer is that the Merkle trees are also propagated, and all the transactions are also propagated, but they don't end up in the final consensus blockchain. So in the blockchain, we just save the Merkle root because we don't have to save the whole tree. Okay. So someone asked, so it's not about whether it's secure? No, it's just this simple property that if you encrypt a message and then you decrypt it and you use the same key, you should get the same message back. Okay, so let me now share my screen and continue with the lesson. So last session was one of the more interesting sessions of this course, where we talked for the first time about blockchain and how blockchain works. And actually, one thing that I have to tell you is that I'm not exactly following what Bitcoin does. So there are some small differences, but I'm basically presenting the conceptual ideas in the same way. So I will later on come back and fill in the small differences that we have with Bitcoin. So for now, I just want to go over the whole process one more time, just from the point of view of different participants in the network. So as I said before, we have a decentralized network, so anyone can do anything that anyone else can. All the nodes are equal. But some nodes decide that they want to become miners and they want to solve that proof of work puzzle, and some nodes decide that they don't want to be miners. And actually, most nodes are not really miners. So I want to just give you an overview of the whole protocol from the point of view of a normal node that is not a miner, and then from the point of view of a miner, so that it gets completely clear for you how the whole system works. Okay? So what does a normal node do? Well, here are the things that a normal node should do. Well, they should first of all establish connections to other nodes. Okay. And generally, the idea is that the more connections you make, the better connected you are. And so you will hear about what's happening on the blockchain and what's happening with the transactions sooner. So it's generally a good idea to try to connect to several other nodes all around the world. Or maybe it's also a good idea to run several nodes yourself if you're, for example, a company that is working with blockchains. So now, what do they do with these connections? Suppose that I have a bunch of nodes on my network. What is it exactly that these nodes do? Okay. So the first thing that they do is propagating transactions. Okay. So what does this mean? This means that whenever someone sends a transaction to one of the nodes, or maybe the node itself is making that transaction. So let's say somehow this node hears about some transaction TX. It will broadcast this transaction to all of its neighbors, and they will also broadcast it to all of their neighbors. This is what's usually called a gossip protocol, because it goes around like gossip, and eventually it reaches everyone. Okay, but I want to get into the details of this, and specifically I want to talk about when a specific node broadcasts a transaction. So if you are a node in this network, and let's say you are honest and you don't want to do anything malicious, and you just received a transaction from another node or somehow received it anyway on the internet, who cares? You know about a new transaction, what would you do? So the first thing that you have to do is that you have to validate this transaction, okay? So when, let's call our node maybe, I don't know, let's call it A. When A receives a transaction, let's call it TX. So these are the steps that A does. First of all, A validates the transaction to make sure it's a valid transaction. Okay, but what does validation mean? So we've talked about when a transaction is valid, and the idea was that, well, it shouldn't create new units of currency, it should have the right signatures, and it should not do double spending. And again, two of these are very easy to check. So checks that it has the right signatures. So let's say signature check. And it also checks that the sum of inputs is greater than or equal to the sum of outputs. Okay, so these two checks are trivial to do, but the next question is, well, when we say it's not a double spend, how do we figure out if this particular transaction is a double spend? So in order to answer that, we have to go back and see what it is that each one of these nodes is going to keep in memory. So normally, and this is not really part of the protocol, so I'm just going to tell you what the normal situation is. It's that the node keeps two things in its memory. Okay. So one of the things that the node always keeps track of is the consensus chain. Or actually, to be more specific, I have to say the longest chain. Right? So longest chain. But to be even more specific, I have to say longest chains, because there might be a fork at some point, and as I said, we might have several valid chains, and then the node will keep track of all of these valid chains until one of them gets longer. Okay, so that's the longest chain or chains. That's one thing that this node keeps in memory. And the other thing is what we call a mempool of transactions. And what this is basically a list of all the transactions that this node has seen, but have not made it to the blockchain yet. So suppose I am the node A, maybe I've seen a transaction, but this transaction has not yet been mined by any miner. It's not on the blockchain, but I've seen it. So I just keep it in my mempool. I just have a set of all transactions that I have seen, but are not yet on the chain. Okay. Now, when I want to validate, part of the validation is, of course, to validate that there is no double spend. Right? So if I have two particular transactions, I can say if they're double spending the same coin, the same output, right? So the question here is that when I'm doing the validation, when I say no double spend, what is the rule? Am I going to only check against the transactions that are already on the longest chain? Or am I going to check against my whole mempool? And of course, I'm going to check with the longest chain because the transactions that are in the longest chain are already on the blockchain, right? So if I have a transaction, let's say Alice paid something to Bob, and this transaction is already on the blockchain, and then Alice tries to pay the same thing to Carol, of course, that's going to be invalid. So if there is a double spend between this new transaction that the node A has received and a transaction that is already on-chain, then this node would just say, okay, this is an invalid transaction, and I wouldn't propagate it any further, because we generally don't want to propagate invalid transactions. It's just an overhead for the network, okay? But actually, in practice, most of the nodes also check the transactions with their mempools and don't propagate anything that has a double spend with respect to a transaction in the mempool. So when I say no double spend, this is with respect to the chain and the mempool. Okay? So in other words, this node knows that, let's say this is the current blockchain, current state of the blockchain. And in each of these blocks, the node knows that there are a bunch of transactions, right? So each of these blocks is a Merkle tree of transactions. And additionally, it also has a mempool, which is all the transactions that this node has heard about, but are not yet in the chain. So when a new transaction TX comes in, the node first checks that the signatures are correct, that the inputs are more than or equal to the outputs, and then it checks that this transaction does not double spend any previous coin that was spent either on the chain or in the mempool. And only if this transaction passes all of these tests, then this node will propagate this transaction further. So the next step is send this transaction, let's say, to all neighbors, which means to all nodes that are connected to you, if and only if the transaction is valid. Okay? So this is what the protocol demands. So any node that does this is considered an honest node. They're following the Bitcoin protocol correctly. But some nodes are actually even more strict than this, and they will add some extra rules. So one of the extra rules that a node might add is that, well, every transaction has a timestamp. So a node might additionally check that the timestamp is not in the future, because if you know the time right now and you see that someone is making a transaction and they're setting the timestamp to the future, they're doing something fishy, right? So as an honest node, you would not propagate that transaction. Another thing that people might check when there are nodes is that maybe the timestamp is too much in the past. So if I receive a transaction today that tells me that Alice wants to send 5 Bitcoins to Bob, but the timestamp on the transaction says that it's for 10 days ago, that's a very weird thing. So many nodes would just ignore these weird things. But there's nothing in the protocol that says they have to do it. So what they have to do is that they have to just validate the transaction, and if the transaction is valid, they send it to all of their neighbors. Okay, so there is a question asked, how do we exactly check for double spending again? Okay, so let me just go to the double spending part. Okay, I'm not sure which one was it. Okay, I had a figure for it. Okay, here it is. So double spending is when you have a transaction that pays some money, let's say to Alice, 5 Bitcoins to Alice. So this is one output of this transaction, right? So this output can be spent only once. But suppose that Alice creates two different transactions, transaction 1 and transaction 2, and then uses this same output in both of them. So once she tries to pay these 5 Bitcoins to Bob and once to Carol. So these two transactions, transaction 1 and transaction 2, are in conflict with each other. Only one of them can be valid. This is what we call double spending. Okay? And as we said before, we cannot really rely on the timestamps here because the timestamps might be fake because Alice chooses the timestamps. So here what we do is that we have a new transaction and we have a set of previous transactions. Well, we have two sets of previous transactions, the ones that are on the blockchain and the ones that are in our mempool. And we just check that this new transaction does not have any double spending with any of the previous transactions. Okay. So another question is, why do we need to check with the mempool? Well, the reason is this. Suppose that Alice wants to do an attack on the network. And let's say that she wants to, for example, do maybe a denial of service attack, or maybe she wants to just jam the whole network. What she can do is that she can create thousands of different transactions and do it such that they all spend the same coin. So instead of just double spending, she can spend the same coin thousands of times. And then she can announce all of these transactions to different parts of the network at the same time. Then if we don't check with the mempool, what happens is that all of these transactions have to be propagated in the whole network. And that's a lot of overhead, even though we know that at the end, only one of them would become valid. Okay, so we check the transactions with the mempool too. Okay. So there is a question that after transaction is validated, will it send to mempool or consensus chain? So I'll answer that, but for, when it's validated, it will be only added to the mempool. But later on, when someone mines it, the transaction goes into the consensus chain. So for now, let's actually write it here. When I receive a transaction and I validate it, I send it to all the neighbors and let's say, and add it to the mempool. Okay. And of course, a lot of the nodes in practice also have a set of invalid transactions that they have seen already, so that if they saw the same transaction again, they don't have to do the validation again. It's kind of like remembering that, oh, I had this, I have seen this transaction before, and of course, they do it using the hash of the transaction. I've seen a transaction with this hash before, and that transaction was invalid. So if someone sends me that same transaction again, I know that I've seen it before, and I just ignore it. Okay. So there is a question that the node only has the transaction. How can it compare with the Merkle root in the chain? So I'll get to that as soon as I go to the next parts of how the propagations work. Okay. Yeah, there is another question that is very similar. How can we check the chain if the transactions are encrypted in the chain? The transactions are not encrypted in the chain. So I'll tell you exactly what's put on the chain in a few minutes. So another question is, why do we need to check that the sum of inputs is more than the sum of outputs? This is, again, because we don't want to be able to create new units of currency. So inputs are the monies that are flowing into this transaction, and outputs are the monies that are flowing out of this transaction. So if the outputs are more than the inputs, that means that this transaction is creating randomly out of thin air some amount of money. And we don't want to let that. Okay. And another question is, if we didn't, then it would keep getting sent even when nodes have already heard it until it gets added to the blockchain. Okay, I didn't understand this one. Okay. So another question is, why not input equal to output? I answered this last session because the difference will be considered a transaction fee and paid to the miner. So I will get to that again in a few minutes, sorry. So the mempool is the queue for propagating the transaction. Not exactly. So everything that is in the mempool is already also propagated by this node to others. The mempool is just like something that this node uses to keep track of the transactions that they have seen but have not made it on the blockchain yet. So that if they saw, for example, the same transaction again, they know, okay, I'm not going to revalidate it and so on. It's already in my mempool. Another question is, so after validation, would transactions from mempool be added to the chain? No, adding to the chain is the work of miners. So a normal node that is not doing mining will not add anything to the chain. And another question is, does everyone have the same mempool? Absolutely not, because the mempool that people have is completely dependent on which transactions they have heard, right? So if you have a node in Hong Kong and someone else has a node on the other side of the world, let's say in Paris, then you will hear many different transactions, and it is very likely that you will have a different mempool at any given point of time. So the mempool is not what we reach consensus on, the blockchain is. And that's the main reason why the transactions that are in the mempool are not really considered to have been processed. These are like, you can think of them as transactions that are in progress. They're waiting for a miner to add them to the blockchain. And only after the miner adds them to the blockchain, the transactions are considered to be processed. Okay, so let me now continue with what else the normal node does. So of course they propagate transactions, but another thing that they do is they propagate blocks. So every now and then, a miner might create a block, and then when the miner creates a block, they will announce the block to the network in the same way that a transaction is announced, okay? So what can happen here is that, let's say our normal node, the node receives a block B. Now, remember, what did the block have? Let's go back here and see what we had in a block. So we have a hash pointer to the previous block. We have the Merkle root of the transactions. We have a nonce, and we have a timestamp. So when I say they receive a block, they receive all of these things, okay? But they also need to validate the block. So this is not enough. If you just receive a block, you cannot validate it. So what happens in practice is that the node receives a block B, and also it receives its Merkle tree. Okay, so both the block and the Merkle tree are propagated in the network. Again, what does this mean? So every block has a pointer to the previous block, and then it also has a set of transactions. But we said that we save this set of transactions as a Merkle tree, but only the root of the Merkle tree is put into the block. Why? Because on the lecture on Merkle trees, I told you that if you only have the root, you can be sure that no one can change the other things, and nothing can change in the Merkle tree without changing its root. So only the root is actually in the block, but in order to validate this block, we need the entire tree. So the entire tree will be propagated. And of course, this block also has a nonce and a timestamp, and the idea was that this nonce should be chosen so that when we compute its hash, the hash starts with a lot of zeros, or the hash is really small, okay? So this is what we do now. So the node receives a block B and its Merkle tree, again, the first step is that I've received the block. I have all the information in the block and also its Merkle tree. Now I want to validate it, right? So the first step is that, okay, let's call this Merkle tree T. You have to validate B and T, okay? But what does this mean? So I already had my chain, right? This is my blockchain that I have saved as a node. This is my local copy of the blockchain, but I know that we are in consensus, so I can kind of be sure that everyone else also has the same copy of the blockchain. So now I'm receiving this block B, okay? So first of all, I have to check to see what is the previous block. So where does this block B point to as the previous block? So maybe B points to the very last place that I have seen here. So if this is done, that's okay. That basically means that the miner is saying add this block to the very end of your blockchain. But it might also be the case that this block B is actually a fork. So maybe it says that my previous block is this one. That's also okay, because maybe this block and the last block that I already had in my chain were mined at roughly the same time. And so maybe we have two consensus chains right now, and we have to wait until one of them gets longer. So if these are the cases, then I would accept that, okay, this block is probably valid. I have to do other validation checks as well. So I would keep this block. But what is one case where the block would be invalid from my point of view? Suppose that this block says that my previous block is all the way down here. So I already, as a node, I know this whole chain, right? And if this new block wants to make a fork down here, then of course that wouldn't be the longest chain, right? So if it's not the longest chain, I can just ignore it because I only care about the longest chain, okay? Only the longest chain is supposed to be the consensus chain. So when we're doing the validation, the first thing is that check that B can be in the longest chain, right? If B cannot be in the longest chain, you just ignore it. And as we saw, there are different ways that B can be in the longest chain. Okay, what else do we validate? Well, the second thing that we would validate is that the hash of B should be small. It should be less than some specific number D, which is the current difficulty of mining a block. And I will get back to how we find D, but for now, let's say that every node knows what the difficulty is. So every node knows what is the threshold that makes a block acceptable. And of course, we want the miner who has added this block to have solved the proof of work puzzle. So the hash of this block should be less than the difficulty factor D that we have. We check that one as well. Okay, what else do we check? The third thing that we have to check is that we have to check that every transaction in this block is valid, because we don't want to let invalid transaction go into our blockchain. Okay, so check every transaction in, okay, now using the block itself, I can't know all of the transactions, but remember that the Merkle tree T is also propagated. So I can know all the transactions using that. Okay, check that every transaction in T is valid. Okay, but now again, we have to talk about how we check validity of transactions. Again, transactions had three things that we had to check. So we first check the signatures, of course. Okay, that's easy. Then we check that the transaction is not creating any new money. So again, sum of inputs should be larger than or equal to sum of outputs. And we also check that there is no double spending. Okay, but there is a difference here. And the difference is that when we are checking for double spending here, the idea is that I want to add this block to my blockchain. Okay, so I check that there is no double spending with respect to previous blocks in the chain. Okay, so let's say I'm adding this block B and there is a transaction in here. Maybe I have another transaction in my mempool that causes a double spend with this transaction, but I don't care about that at this point. I only care that this transaction that is going to be added to the chain using this block does not have any double spending with any transactions that come before it somewhere in the chain. Okay? Why is that? Because basically the transactions that I have in my mempool don't matter at all. These are transactions that are not finalized. These are transactions that are not yet on the chain, right? So when I'm adding a new block to the chain, I don't need to check with my mempool. I shouldn't actually check with my mempool. I should only check with the previous transactions that were on the chain. And specifically, it's important to say that previous blocks in the chain, not all blocks. Like, so, okay, let's say I have a transaction that is in this block B, okay? And let's say that the previous block of B is this one. Then I only have to check with transactions that appear in this block or the blocks before it for double spending. If there is another transaction here, for example, that double spends with the original transaction in B, that's still fine, because in the end, when one of the two chains gets longer and becomes our consensus chain, only one of these two blocks will remain. So only one of these two blocks, only one of these two transactions that were double spending the same coin will remain in the consensus chain, okay? So you only check with the transactions in the blocks that are appearing before B. So you take B, you take the hash pointer that goes to the previous block, and then the hash pointer there that goes to the previous block, and so on. And you only check with transactions that appear in these blocks. And of course, not only with respect to transactions in the previous blocks, but also with respect to transactions in B itself. So I don't want to have two transactions in this new block B that are double spending the same coin. That's also unacceptable. So I would say no double spending with respect to B itself, or with respect to transactions in B itself, or any previous block. Okay? So this is how I do the validation for blocks. And again, if the block was valid, then I just send it over to everyone. Okay, so send B and the Merkle tree of transactions T to neighbors if and only if it was valid. Okay. So any questions here? Let me just look at the questions. So there is a question that, can you explain the part about checking mempool for double spending again? Yes. Okay. So you see, there are two things that a node would receive and propagate. There are transactions and there are blocks, right? So when we receive a transaction, we want to make sure that this transaction is valid, that this transaction has a chance of eventually getting on the blockchain, right? So what we do is that we validate that its signatures are correct, that it doesn't create any new units of currency, and we want to also validate that this particular transaction does not do double spend with any of the transactions that we have already seen. So I want to make sure that all the coins that are used in this current transaction that I'm seeing right now are unspent. They've never been spent before, okay? So the way I check that is that I just go through all the transactions that I've seen before, no matter if they are already on the blockchain or just in my mempool. And if I see a double spending, I say that this new transaction that I received is now invalid from my point of view. So I will not put it to my mempool, and I will not tell the other neighbors about it. Maybe I can have another mempool for invalid transactions, and I just add it there, okay? So that's the idea for when you're propagating transactions. And again, the reason that we check against the mempool is to avoid attacks on the network where someone creates a lot of invalid transactions and wants to just overwhelm the whole network with a lot of messages, okay? So that's the part about propagating transactions. But now suppose that I receive a block. So if I receive a block, that means that some miner has solved the proof of work or is claiming that they have solved the proof of work puzzle. And now they have sent me a block. And of course, in order to validate this block, it's not enough to just have the block. I should also have the Merkle tree of all the transactions in this block. So I receive both of them together. And what do I do? In order to validate it, I have to check several things. I have to check that, well, first of all, this block has a chance of being in the longest chain because only the longest chain matters. Secondly, I have to check that it has the right hash. If the hash is too large, it's not a valid solution to the proof of work, so I can just ignore it. Thirdly, I have to check that every transaction here is valid. But now this validity check is a bit different from the validity check that I did for transactions. Because now what's in my mempool doesn't matter anymore. The only thing that matters is what is actually on the blockchain. So for every transaction that appears in this block, I have to check that it has the right signatures, that it doesn't create new money, and that it doesn't do double spending. But when I say it doesn't do double spending, I mean that it doesn't do double spending with respect to other transactions in the same block and in the blocks that came before it. So it's fine if I have something in my mempool that is doing double spending with something in this block. That just means that the transaction that is in my mempool becomes invalid now. And the transaction that is in the block is added to the blockchain, that one becomes valid. Okay? So, and if all of these checks passed, I just sent the block and its Merkle tree of transactions to all of my neighbors. And there is one more thing. There is one more step. Let me just call it last step. I update my mempool. What does it mean to update my mempool? Well, there are several cases where you have to remove a transaction from your mempool after you add a block, right? So one case is that suppose that I had a transaction and this transaction actually went into a block. So I don't need to keep it in my mempool anymore, right? So if a transaction is already in this block, I'm not going to write this. If a transaction is already in this block, I just don't need to keep track of it anymore. Another case where I have to maybe update my mempool is that maybe I had a valid transaction before, but because of the transactions that are in this mempool now, that are in this block, then some of the transactions in my mempool became invalid, right? So I will just not work with these invalid transactions either. But generally, this is not something that the protocol specifies. So as a node, you can decide what you want to keep in your mempool and what you don't want to keep in your mempool. And many of the nodes just keep everything in their mempool. And the rule that they say is that, yeah, I keep all transactions for today in my mempool. And after a day, I'll say that this transaction has expired. And I don't really update my mempool. That's fine. There's no problem with that. You can just keep your mempool as long as you want. Okay, so this is a voluntary step, so I would remove it now because it's not necessary in the protocol, but most nodes do it. Okay. So this is how we propagate transactions and how we propagate blocks. And of course, just to emphasize more, I've already covered this in the propagation parts, but every node also keeps track of the blockchain. And what this means is that they keep track of the longest chain or the longest chains. And actually, it's a good idea to keep track of some of the chains that are not the longest, but close to the longest. For example, here's a scenario. Let's say that I have this chain. Okay. And let's say that I know that this is the longest chain for now. Okay. And then I see a fork. I see two blocks that are both added to the end of this chain. And now I have two longest blocks. So I'm keeping track of both of them. But then suppose that one of them gets longer. For example, this one gets longer. Okay. As I said before, I would assume that the longest chain is the consensus chain. So now I assume that this one is my consensus chain. Okay. But maybe I shouldn't really delete this one from memory, because it might happen that in the future, this is very unlikely, but it's not impossible. It might happen that I get two blocks added here, and then actually this one becomes longer, right? And all the protocol tells me is that the longest chain is the consensus chain. It doesn't really tell me as a node which chains I have to keep track of. So if I just remove this chain down here as soon as the chain up there got longer, then I might actually lose track of the longest chain. So one thing that most nodes do is that they keep track not only of the longest chain, but also of all the chains that are almost the same length. Okay, so if you have a chain that is like 2 blocks shorter than the longest chain, it's a good idea to still keep track of that, because there is a small chance that later on it becomes your longest chain. But at some point it becomes very unlikely and you just stop keeping track. So for example, if let's say this chain gets so much longer, maybe it gets 5 or 6 blocks longer than this chain, then there is very little chance that this chain can again get longer and actually keep up and become the consensus chain. So at this point, it's safe to say this is not going to be the consensus chain. I'll remove this one from my memory. But generally, it's a good idea to keep track of not only the longest chain, but all of the chains with almost the same length. So I just write it here, all chains that are almost the longest. Okay. So let me now answer some of your questions. So someone asked, what's the difference between a node and a block? Well, a node is like a computer on the network. You can run a node. You can use your laptop as a node. A block is what we put in the blockchain, right? It's our unit in the blockchain, which is this whole thing that had a hash and a pointer to a previous block and also a set of transactions. Okay. So someone else asked, is it possible that when we want to add the block B, we haven't seen B's predecessor? Yes, that's actually technically possible, but it's very unlikely, because at least in Bitcoin, what we do is that we set the difficulty so that a new block is found roughly every 10 minutes. And what that means is that I had 10 minutes to see this predecessor. And with the levels of connectivity that we have on the internet today, it's kind of unlikely that I don't see the predecessor in those 10 minutes. So I would say we're safe in that case. But anyway, even if that happens, if your connectivity is not so good and you think that might happen, you can just have also a mempool of blocks that you have seen, and you can wait until you see the predecessor as well, and then add them in order. Add the predecessor first and then add this block. But that's only if your connection to the network is really bad. Okay. So another question is that miners can only add validated transactions from the mempool to the blocks. Then why do we need again check that all the transactions in the new block are valid? Well, the reason for that is that, as I said in the very first session of this course, we want to have a trustless system. We don't want to trust the miners. So the miner is just a node, and that node has its own mempool. And I'm not going to trust that the miner is not malicious, that the miner is going to do the right thing and only include valid transactions. I'm going to always verify it. So every node on the network verifies that the block that is announced is actually valid, and would add it to their copy of the blockchain only if it is valid, if every transaction in there is valid. So we don't trust the miners. Okay. So another question is, if A and B both have some transaction in the mempool and not on the chain right now, and then A mined it and added to the chain, so B should kick the transaction out of B's mempool, right, to prevent double add. Yes, that's something that is advised, but in practice, many of the nodes are just lazy and don't do that. So many of the nodes just keep their mempool, because what happens if you have a mempool that is larger than what you should actually have? What happens if you have extra transactions in your mempool? The only thing that happens is that you might reject some valid transactions, but most nodes are fine with that. So they don't care that much. But technically, what you say is true. So you have to update the mempool after you add a block. And the update is basically that every node, every transaction that is in this current block should get out of the mempool. And also every transaction that is in your mempool that has a double spend collision with one of the transactions that is now added to the blockchain in this block is now invalid. So you have to remove the invalid transactions from your mempool as well. Okay. Oh, and by the way, this is again something that the nodes can decide for themselves, but there are many nodes that would store even the invalid transactions in their mempool. And they just say that if a transaction was invalid, I add it to my mempool, but I don't announce it to my neighbors. So again, the mempool is not something that is really an important part of the protocol, in the sense that the mempool is not shared with anyone. Each node has its own mempool. So you can do whatever you like with your own mempool. Okay, the only thing that we want to make sure is that if you are an honest node, you don't propagate too many double spending, too many transactions with double spending attacks. So that's the most important thing. But the only thing that we have consensus about is the blockchain. So only the transactions that are on the blockchain are considered to be processed and done. And transactions that are in your mempool don't mean anything to anyone, and you don't have any kind of consensus over the mempool with anyone else. So you can manage your mempool as you like. Okay. And yeah, we are out of time. So this is the end of this session. In the next session, I'm going to talk from the point of view of a miner, and I'm also going to consider some other details. I will stay and answer all the questions, but you guys can leave. Okay. So another question is, if A and B both have some transaction in the main, okay, I answered this one, sorry. Another question is, will the memory used for checking double spending become large when the chain becomes longer? Yes, in a sense, because, Okay, how do you check double spending? The way I told you about the protocol is that you have to just go and check every transaction. But actually, an easier way to do it is to just have a set of all the outputs or all the coins that are already spent. And of course, we can use their hash so that we can easily check if a particular coin is in the set. So when I see a new transaction, I just check that all of its inputs are unspent, that no one has previously spent these inputs in another transaction. And then I would just mark all of them as spent. So all I need is that I need to have a set, let's say, of hashes of all the coins that are currently not spent yet. And whenever I add a new transaction, I would update the set and say, okay, these coins are already spent now. And whenever a transaction goes into the blockchain, it of course creates a bunch of new nodes, a bunch of new coins, which are the outputs of the transaction. And we will then add them to our set of unspent coins. Okay. So another question is, how do we check the validity of a transaction if the mempool is different for different people? Won't there be conflicts? Yes, there will be conflicts. Basically, if you have different transactions in your mempool, what happens is then, okay, suppose that we are two different people and we have different mempools. And let's say that Alice creates two transactions that double spend the same coin and sends one of them to me and one of them to you. So what happens is that at first we see the first transaction and both of us think that this is valid. We add it to our mempools and then we start propagating it. And then eventually each one of us will hear about the other transaction. But then one of us would say that the first transaction was valid and the second was invalid. The other one would say the opposite. So there is no consensus about the mempool. Okay, another question is, does everyone keep a copy of the whole chain? If so, how to make sure everyone has the most updated chain at the same time? So here again, there are several different questions actually in here. So all the normal nodes will keep copies of the whole chain. And the way that we make sure that they agree on it is that, of course, we have proof of work and we have this rule that the longest chain is the consensus chain. And as I said in the previous session, it's very unlikely that you keep having the longest, several longest chains for a long time. So after a while, the longest chain stabilizes and you can be sure that this is the longest chain. I'll actually talk more about consensus and how long you have to wait for it, probably in the next session. But it's not that they have the same chain at the same time. It's just that eventually they will reach a consensus about the chain. Right? So for example, again, think about it like this. When this block B is announced, some nodes, of course, hear about this block B sooner than others. So of course, they will add this block B if it's valid to their chain sooner than others. So there is a point in time where people have different views of the blockchain. But eventually, if this block happens to be in the longest chain, everyone will agree that this block is on the blockchain. Okay. Another question is, what happens to a new miner or a new node who wants to join? How do they get the previous chain of blocks? Well, they can just ask another node to give it to them. And these days, there are a lot of websites that have APIs and give you the whole history of Bitcoin. So that's also quite easy. And actually, there are many nodes that provide this service. So if you download the Bitcoin clients, your Bitcoin client will automatically download all of the history of the chain. And that's very easy. Okay. Another question is, what's in it for normal nodes to help secure the network? For miners, they have rewards, but are there rewards for validation and propagation of transactions? No, there are no rewards for validation and propagation. What's in it for normal nodes, we will see later, but I can tell you that I can give you one example. Suppose that you are an online shop, and suppose that you want to accept Bitcoins. So you will run a normal node, and ideally what you want is that you want to know about the transactions that are propagated and the blocks that are propagated as soon as possible. So you like to take part in this. But again, there are no incentives. There isn't really no, let's say, reward in Bitcoins in the same way that there is for miners. And the reason there is no reward here is that what the normal nodes do is not that hard. They're just receiving some transactions and propagating them. You can easily do it on a normal laptop. It doesn't take that much computational resources. So a lot of people would just do it voluntarily. But if you consider what a miner has to do, they have to solve a really expensive proof of work puzzle, and solving that uses a lot of electricity. It really needs a lot of money. So for them, we actually need to pay. You cannot have a volunteer miner. Okay. Another question is, how do the nodes decide when to drop the other chains? It's up to them to decide at which point they want to drop. Almost everyone uses some standard implementations. So there's, for example, the Bitcoin Core implementation. So the answer here would be that almost all of the nodes do what the implementers of Bitcoin Core have decided to put into their code. But in practice, again, it doesn't matter that much. The idea is that as a node, you just want to make sure that you're not dropping something that might later become the longest chain. And if you wait, for example, for the difference to become, let's say, 6 blocks or 10 blocks, then you can be pretty sure that this is going to remain the longest chain, and you can then drop everything else. Okay, another question is, for homework 1, exercise 2, which lectures do you recommend us to look at? Look at the lecture on symmetric cryptography. Okay, another question is about validity of a symmetric encryption scheme. Yeah, so validity is not the same as security. Basically, when we say it's valid, the only rule is that if you encrypt something with a key, you can decrypt it with the same key and get the same original message. That's what validity means. Okay. So another question is, how do you actually check transactions with previous blocks to make sure it's valid, since blocks only keep the root of the Merkle tree, right? Yes, all the previous blocks. So what goes in the blockchain is only the root of the Merkle tree. But what's propagated is the block, which contains the root hash and also all of the tree. So as a node, it's true that only the root of the Merkle tree is in your blockchain, but you also have received the Merkle tree and all the transactions in it before. So you just have it in memory and you can check it. Okay. Another question is, to check whether one transaction is valid in the block will consume order log n hashes. Well, if you have n transactions in a block, checking whether a particular transaction is in that block takes order log n. But in practice, again, when we want to check the validity, what we do is that we just have another set of unspent coins or unspent outputs, and we just check that this particular transaction is not using any of the outputs that were previously spent. So we just check that all the inputs come from the unspent outputs. Okay, so it's just the order of the number of inputs of the current transaction, because we just have to check that their hashes were not seen before. Okay. So another question is about the homework. So in the rock, paper, scissors case, should I assume that the malicious users will not steal the original digest packet and change it from sender. So no, you can't really assume that. Well, you can assume that the messages will be delivered, but maybe a malicious party, for example, the ISP of Alice or Bob, changes the messages. So maybe the message that you receive is fake, and you have to check for that. Okay? So another question is, can the transaction choose which block they're in, or just the newly mined block? Generally, the transactions cannot choose which block they want to be in. The only thing that they can do is to say, okay, this is a transaction, this is how I want to transfer money. And then the miners decide which transactions to put into their blocks. So miners have complete control over creating the blocks. There is a small caveat to this. Actually, one of the details of Bitcoin is that you can specify a block number in your transaction and say that that this transaction is valid only after this particular block number. So suppose that you want to say, let's say Alice wants to pay Bob, but Alice is only willing to pay Bob after, let's say, 2 days. So what Alice can do is that she can create a transaction, and in that transaction in Bitcoin, she can basically put a block number and say that this transaction can only be mined if the block number is after this particular number, which is equivalent to saying this transaction can only be done after a particular time, since every block comes in roughly 10 minutes after the previous block. But that's just the detail of Bitcoin. In general, the answer is no, the transactions cannot choose which block they're in. Only the miners can choose, because whenever you're a miner, we will cover this in the next session from the point of view of the miners. You have a mempool of valid transactions, and you are the one who gets to choose which transactions to put into your block. Okay. So we again have a question about the rock, paper, scissors, I think. So the question is, if the middleman always changes the digest, then Alice's message never can go to Bob correctly. How to count the time of my protocol? So in this case, you can just say that your protocol maybe fails, but if it fails, it should fail with an acknowledgement that there was some malicious middleman that was changing the messages, or maybe one of the parties was malicious. So the idea here is that, again, in the homework, I don't expect you to cover all the cases. What I expect you to do is that I want you to give me a protocol where they can play rock, paper, scissors, and they cannot cheat. And if anyone is malicious and sends messages that don't make sense, for example, let's say Alice sends a message to Bob, and then Alice's ISP changes that message, then the protocol should fail. And everyone should know that the protocol has failed. Okay. Another question is, if the miner purposely tampers with the transaction order, will it be able to cause some other transactions to be invalid? Yes. So again, miners have a lot of control. Let me go back to this example that we had here. So let's say Alice is doing this kind of double spending. She's spending the same coin twice in 2 transactions, transaction 1 and transaction 2. In effect, what this means is that both of these transactions are sent to the network, and each of them is propagated to a portion of the network, right? So maybe some nodes have seen transaction 1 and decided that transaction 2 is invalid, but some other nodes have seen transaction 2 first and decided that transaction 1 is invalid. So let's say this has happened. And let's say you're a miner. Most miners usually don't run just one node. They have many different nodes in different countries so that they have a good connectivity. So if you're a miner, it's very likely actually that you have seen both of these transactions. And if you have seen both of these transactions, then as a miner, you have a choice. you can choose to put transaction 1 in your block, and then if your block gets added to the blockchain, transaction 2 becomes invalid. Or you can choose to put transaction 2 in your block, and then if your block is added to the blockchain, transaction 1 is ignored and it's invalid. So in a sense, when we have double spending, it's the miner who's choosing which one is valid and which one is invalid. But again, we don't have a single miner. We have many different miners. So maybe there is a miner who is putting transaction 1 in their block and a miner who's putting transaction 2 in their block. And then it's a proof of work competition. Whoever gets to add their block first to the blockchain makes the other transaction and the other block invalid. Okay. And generally, one more point that I would say here is that if one of these transactions have a higher transaction fee, then it's very likely that the miners will choose the one that has the higher transaction fee. Because of course, the miners want to make as much money as possible. Okay, any other questions? I'll stop the recording now.